Lab 4, Oscillations. The main purpose is to apply Newton's laws of motion to the real world. The experiment today involves the motion of an object while oscillating on a spring. We'll be measuring its motion and create a model to measure its energy changes as well, and we'll be using the energy principle. We can take our video and load it into Tracker. As you can see, the origin is defined where the spring is attached, and the spring is oscillating in the X and Y direction. We can take this video and data created from Tracker and use it to compare to the computational model. Before we create the computational model, we must first make a few assumptions. For one, the system is a spring, mass, and the Earth. The surroundings are none. Since this is true, there are no outside interactions on the system, thus the total energy is constant. We assume that the mass of the spring is negligible, and the initial speed is 0 meters per second. The mass of the object is 0.402 kilograms, the spring constant is 6.83 newtons per meter, and the initial length of the spring is 0.123 meters. Then we initialize our ball mass as defined before, and initialize our initial position from the data taken from Tracker. And since our initial velocity is 0, we do that here. And then the gravitational constant of Earth, which is 9.8 meters per second squared, and these two other values are from our assumptions. Then, to calculate the force of the spring, we use the L value, which is essentially the ball position, or the object's position, minus the spring position, with this diagram here. Then we calculate our L hat vector, which is essentially the unit vector, and then our displacement, which is the length of the spring minus the initial length of the spring. Then we can create this while loop, where t iterates up to 9.4 seconds, which is the length of our Tracker video. We initialize our energies. Then to update our energies, we use the idea that the kinetic energy is equal to 1/2 mv squared, which we plug in right here. Potential gravitational energy is mgh, which we plug in right here. And then the spring potential energy, which is 1/2 k s squared, where k is the spring constant, and then s is the displacement, which we plug in right here. And then to calculate the total energy, we simply add up all these three energies. Then to calculate the force of gravity, we know that force of gravity is equal to negative mg, which we plug in right here. Force of the spring is negative k, which is the spring constant, times the displacement times the L hat vector, which we plug in right here. And then to calculate the net force, we simply add up these two forces. Then we use Newton's second law to determine the ball's velocity, and then update the ball's position using the ball's velocity. Then, to calculate the change of energies, we simply take each energy and subtract it by its initial energy. Then, using the energy principle, we can determine that the change of energy in our system is equal to the change of kinetic energy plus the change of spring potential energy plus this change of gravitational potential energy. And as you can see with our model, it does closely resemble our video in Tracker. We can take this data created from the computational model and compare to our Tracker data. As you can see in this energy time graph, the change in kinetic energy is in blue, the change in gravitational energy is in red, the change in spring potential energy is in green, and the change in total energy is in orange. With our X and Y position time graphs, we can see that they do closely resemble each other, the model in blue and the experimental in red. The two graphs do resemble each other, but there are some discrepancies. This can be highlighted for two reasons. For one, the variance in the Tracker data, which could be fixed with simply collecting more data points or more frames in the video. And two, the drag force, and we can add this drag component to the computational model if we want to reduce the discrepancy. Now, what does it mean? Is the energy principle satisfied? By the energy principle, we know that the change of energy is equal to all these components. And since it states that the energy of the change of the energy of the system is equal to the change of energy of the surroundings, since there's no external work on the system, we know that the energy of the surroundings is 0, and over here we do see that the change of energy is equal to 0 on this graph. Now, if we compare the period of oscillations between the X and Y positions, we can see that with the period of oscillation in the X, we get 1.59 seconds, and then for the Y, we get 1.52 seconds. We see that the Y is less, and this is due to the fact that the masses change differently in each direction. For example, in the Y direction, gravity is the sole actor, and for the x direction, the spring is more determinant of its movement.